Starting recording. So, good day, everyone. We are the Group 1 and we are here to present this lesson, Adiabatic Flame Temperature. So, ano nga ba yung adiabatic flame temperature? The maximum temperature will be greatest if there is no heat loss experienced during combustion. And this is known as the adiabatic flame temperature. The adiabatic flame temperature is attained during complete combustion. Here is the working equation for adiabatic flame temperature. This is just like the energy balance, and here is the product in the left side and the reactant is in the right side. Next is the three methodologies to calculate the adiabatic flame temperature. The first one is to be discussed by Mr. Carlo Reyes.
In the three methodologies to calculate the adiabatic flame temperature, for number one, we have the constant average specific heat. As we can see in the working equation, the average specific heat is used for the product side since the temperature at the reactant side is known and its specific heat can be easily calculated. Next slide. Still, for the part of constant average specific heat, using the constant average concept of the specific heat, then the sensible enthalpy of the products can be expressed as in the figure. The average the average specific heat is taken at the average temperature of the reactants and the products. This procedure is accepted until the change in the temperature is in the order of 20 Kelvin.
The next one is iterative enthalpy balance. The enthalpy of reactants is known. The word equation may be in the form of initial guess of flame temperature is used to identify the enthalpy of the product. If HP if HP1 times TP1 times HR times TR, then a higher flame temperature is used TP2. This process is repeated until HP1 times TP1 is HR times TR is B2 times TP2. Linear interpolation can be used to identify the adiabatic flame temperature.
For the equilibrium state determines the species concentration and temperature under certain constraints such as enthalpy, temperature, and pressure, and will naturally yield lower value than those used in method 1 and method 2. At higher temperatures, the particle lose kinetic energy due to dissociation and ionization. Dissociation is the phenomena where the molecules form separate atoms due to collision while ionization and the outer electrons are separated, creating ions. This phenomenon changes the composition and the product of combustions, which are not reflected by the linear relations of internal energy and temperature.
So good day. Here are now the example problems that we're going to So the example number one. Estimate the diabatic flame temperature of a constant pressure reactor burning a stoichiometric mixture of hydrogen and air at 101.3 kilopascal and 250 degrees Celsius at the inlet. So we're now going to uh, So we are now going to present the solution. The combustion formula is stated in the presentation: H2 plus 0.5 quantity O2 plus 3.76 N2 quantity, and the product side H2O plus 1.88 N2. Let us assume that the water in the product side is in gaseous phase. Since the reactant are H2, O2, and N2, all are stable elements, then its enthalpy at STP is 0. The reactants enter the reactor at 25 degrees Celsius. So there is no sensible enthalpy. Thus, enthalpy reaction is equals to 0. So now we're going to calculate the constant specific heat. Assuming a constant specific heat at 1800 Kelvin for water, specific heat is equals to 49.7 kilojoule per kilomole Kelvin. For nitrogen at 1800 Kelvin is equals to 35.59 kilojoule per kilomole Kelvin. Next slide, please. So, stated in the presentation, we're now going to calculate for the product temperature. 298 Kelvin plus 0 minus kilomole H2O over kilomole hydrogen quantity negative 241820 kilojoule per kilomole H2O over 1 kilomole H2O over kilomole H2 quantity 49.7 kilojoule per kilomole H2O Kelvin quantity plus 1.88 kilomole N2 over kilomole H2 quantity 35.59 kilojoule per kilomole N2 Kelvin quantity, and the specific or final temperature of the product is equals to 2371.6 Kelvin. Now we're going to calculate for the average temperature. Temperature of the product plus temperature of the reactants divided by 2 is equals to the temperature average. So substituting the values, 2371.76 plus 298 divided by 2, we're now going to have the value of the average is equals to 1334.88 Kelvin. Thus, it is equivalent into 1350 Kelvin. Next slide, please. The calculated average temperature is significantly lower than that of the assumed value. Using the average temperature, the flame temperature will be recalculated as stated in the table in the presentation. The change in the average temperature is 11.96 Kelvin, which is below the set condition of 20 Kelvin. The adiabatic flame temperature calculated is at 2478.02 Kelvin. So, next slide, please. So, using the iterative enthalpy, we're now going to use for the main formula of adiabatic flame temperature as stated in the presentation. And in the derivation, we're now getting the final equation that we're going to use. Next slide, please. Now, choose the suitable temperature. Let's assume that the temperature that we're going to use is at 2000 Kelvin. Then, inputting the 2000 Kelvin and 2700 Kelvin in table. If enthalpy product quantity temperature product is less than H or enthalpy reactant quantity temperature reactant, then choose the higher value of TP or choose the higher value of the temperature of the product. By linear interpolation, where the enthalpy of the product is equals to 0, then temperature of the product minus 2000 divided by 2700 minus 2000 is equals to 0 minus quantity negative 63495.6 quantity divided by 2000 21,652 minus negative 63495.6 quantity. And we're now getting uh, the temperature of the product, 2522 Kelvin. Next slide, please. So now, the example number 2 would be presented by Eliser Flores. Eliser Flores.
Our example number two states that liquid octane, or CHH18, enters the combustion chamber of a gas turbine steadily at 1 atm and 250 degrees Celsius. And it is burned with air that enters the combustion chamber at the same state. Determine the adiabatic flame temperature using iterative method for A. Complete combustion with 100% theoretical air. B. Complete combustion with 400% theoretical air. And C. Incomplete combustion in the products with 90% theoretical air. Next. Our solution is for the first one, which is for 100% theoretical air, we have liquid octane plus 12.5 multiplied by oxygen plus 3.776 nitrogen is to 8 carbon dioxide plus 9 water plus 47 nitrogen. And our formula is below. For the Q reactants, oxygen and nitrogen are stable elements and will yield zero, as can be seen from the table below. Next. Our working equation will be stated below. And below that is the final equation that we have derived. For a good assumption, the approximate enthalpy is around 79,290.5 kilojoule per kilomole. For carbon dioxide, that is about 1,800 Kelvin, water is at 2,150 Kelvin, and nitrogen at 2,650 Kelvin. The first assumption is at 2,200 Kelvin, as can be seen in the table. Then, using linear interpolation to solve, we have the temperature of the product minus 2,200 divided by 2,500 minus 2,200. It is equals to 0 minus negative 519,750 divided by 285,020 minus 500, negative 519,750. And our temperature of the product is at 2,393.75 Kelvin. For letter B, which is for 400% theoretical air, we have liquid octane plus 50 multiplied by oxygen plus 3.76 nitrogen is to 8 carbon dioxide plus 9 water plus 188 nitrogen plus 37.5 oxygen. Next. Then our working equation will be stated below. And as usual, the derived formula that we have come up is also stated below. Then, for a good assumption, the approximate enthalpy is around 20,930 kilojoule per kilomole. For carbon dioxide, it is about 750 Kelvin. Water is at 900 Kelvin. And nitrogen at 1000 Kelvin. And oxygen is at 950 Kelvin. The first assumption is at 900 Kelvin, as can be seen in the table below, where 900 Kelvin is in the first row. Next slide. Then, using linear interpolation again to solve, we have the temperature of the product minus 900 divided by 1100 minus 900 equals to 0 minus negative 505,585 divided by 113,000. 1,135,625 minus negative 505,585. And our answer will be 961.61 Kelvin. For the last letter C, which is for 90% theoretical air, we have liquid octane plus 11.25 multiplied by oxygen plus 3.76 nitrogen is to 5.5 carbon dioxide plus 9 water plus 42.3 nitrogen plus 2.5 carbon monoxide. Next. Our working equation will be as follows. And at the bottom, we can see the final equation that we have derived from our first one. Next. For a good assumption, the approximate enthalpy is around 73,640 kilojoule per kilomole. For carbon dioxide, that is about 1,700 Kelvin. Water is at 2,000 Kelvin. Nitrogen is at 2,500 Kelvin. And carbon monoxide is at 2,450 Kelvin. The first assumption is at 2,100 Kelvin, as can be seen below, and the last assumption is at 2,500 Kelvin. Then finally, using linear interpolation to solve, we have the temperature of the product minus 2,100 divided by 2,500 minus 2,100 equals to 0 minus negative 451,976 divided by 526,010 minus negative 451,976, and our temperature of the product will result in 2,284.86 Kelvin. Next. Please look at our graph below. Our graph states that the maximum adiabatic temperature is when there is a stoichiometric combustion. For lean mixtures to stoichiometric mixtures, the adiabatic flame temperature can be predicted easily with the above methods, and the value is close to each other. As for rich mixtures, the value varies significantly from different methods.
Thank you for listening. We are the group one. That's the end of our presentation.